Today we are going to continue our discussion on surface integrals, and then also we'll have integrals in R3 like the triple integrals, correct? And we will be talking about in this last lecture these two important theorems, the Stokes theorem and then divergence theorem. Also it's called Gauss divergence theorem, okay? And this is the motivation for both these results. We have kind of already discussed when we were talking about Green's theorem, so I will recall certain things. So the idea is more or less the same, and of course the fundamental theorem of calculus, okay? So we start with the Stokes theorem. So let us see that what does it do. So you remember in Green's theorem what happened? We had a relation between a double integral and the line integral, correct? Where this double integral was over a domain in the plane, xy plane, okay? So now this statement is basically it's going to do something similar, the Stokes theorem. So what we are going to have surface integral. So surface, it's a surface in R3. So we are talking about integral of functions over surfaces, isn't it? So this theorem, what it basically does, you consider a surface integral over some nice surface and then look at its boundary curve, okay? So you have a piece of surface and then imagine the boundary curve. So what does this theorem do? Basically it gives you a relation, okay, like we had in the Green's theorem or in the fundamental theorem of calculus, that the integral over the surface is given by or giving in terms of the integral of some other function which will come from the vector field over the boundary curve, okay? So this is precisely we had this situation in Green's theorem also, like you wanted to integrate things over a domain and then the integral can be transformed or I mean of course the function changes because the derivatives come in the play and you get a line integral to do. So what we consider, as always, we had defined the oriented surfaces. So you look at or you consider a positively oriented surface, okay? Then so just imagine this picture, okay? So this is the boundary curve, and then imagine this is the surface which has the positive orientation. That means the normals are pointing outward. Then automatically what happens, that on this curve also you get an orientation, okay? And namely this orientation is such that if you move along, okay, so it's written over here that this orientation of S, it is going to give or induce a positive orientation on the boundary curve, okay? What does it mean? It simply means that if you move in the positive direction along this curve, okay, so if you walk in the positive direction around this curve, then your head is always pointing in the direction of the normal vector, okay, the outward normal vector. So this is what the positive orientation on the surface induces an orientation on the curve, okay, which is a positive orientation, and the meaning of this is precisely what I just said, okay? So then this theorem basically says that if I have an oriented piecewise smooth, as you know, I mean we allow piecewise smooth surfaces, then that is bounded by a smooth and simple closed curve C, okay? So basically you have a surface and then you have the boundary curve. This curve is piecewise smooth and simple closed, okay? That means it meets at the end point and it has the positive orientation, okay? And if I have a vector field over this such that the component functions which are they have the continuous partial derivatives, and these derivatives they make sense in a slightly larger region containing the surface, okay? Then the surface integral of this, the curl f, okay? So you know this is going to give you the tangential component of I should say here. So this integral which is over a surface is precisely the line integral over the boundary curve, okay? And you remember what is this? This is precisely as we had in the Green's theorem. It's just that now we have the curve in the space, okay? Earlier in the Green's theorem when we were dealing with, the curve was in the plane, and if you rewrite this in the parametric form, then this is nothing but the line integral of the tangential component, okay? Remember this? So this is precisely the same situation as we had dealt with in the in the Green's theorem is just here that we are in high dimension. Okay, and of course I mean I have written it here, this is the parameterization. So you have this curve, it has a parameterization with positive orientation, and I will not really talk about the proof, and you can easily relate that the surface integral is now being done in terms of line integral. Okay, so here you have the curl, why the curl thing comes in and so on, correct, because we are dealing with this integral of the tangential component. Okay, so there are some remarks, as I said here, like the surface integral is being given in terms of the line integral on the boundary curve. So the first remark says that the shape of the surface is not really important, it doesn't really matter as long as the curve, boundary curve, remains the same, because finally the integral is in terms of the line integral over the boundary curve. Okay, so this is precisely the situation which we we have talked about when we were doing Green's theorem, or when we tried to discuss the fundamental theorem of calculus. Is the endpoints for such situations, they play a role. Okay, and this is again the same thing, that this involves the tangential component of the line integral. This is, I mean, so you go back to your Green's theorem and try to compare it, and not only that. So if we have this surface, okay, if I consider this surface to be flat, that means this lies in a plane. So for example, it lies in the xy plane. So now we should get back our Green's theorem, and this precisely happens. So if I consider a flat surface in the xy plane, then the normal vector is going to be, the outward normal is going to be decided by the positive k direction. And then what happens, then the surface integral, actually it becomes a double integral, because now you are in the xy plane. So this is what you get, this is like double integral. So imagine, I mean, this s is written as d, okay, and then this is the area component. This is precisely the statement of Green's theorem, because now your surface is sitting in the xy plane. That was what we considered in the Green's theorem. Okay, so this is higher dimensional generalization of Green's theorem in a way, correct? Because now you are considering the surfaces rather than just the domains in the xy plane. Okay, and one more thing which is very important. So you imagine a closed surface. For example, you think of a sphere or an ellipsoid and so on. Okay, then what happens, now you have a closed thing, so you don't have a boundary curve, because it doesn't have a boundary. I mean, it's not just bounded by a curve, that's correct, I mean boundary in that sense. So what happens is, in such cases, this integral becomes 0, and why? I mean, you can just apply the Stokes theorem. So what you do is, you cut this sphere or any other surface, closed surface which you start with, you cut it into two pieces. Okay, so now you are going to get the common boundary curve for both the surfaces. But when you give them the positive orientation, the whole surface you give the positive orientation, then automatically what will happen, that the induced orientation on C, on the boundary curve, okay, will have opposite signs. Okay, will be opposite when I go from one surface to the other surface. Okay, so they cancel each other. This is something which we had done during our study of Green's theorem, and correct. So then the net result is just going to be 0, because there's going to be one thing with positive sign, and one is going to be the opposite sign, so they will cancel each other. Okay, so this is where you have to be careful, that if the surface is closed, then you can easily conclude that the surface integral of the curve, okay, this is the normal component. All right, so let us work out some examples. Okay, so use Stokes theorem. Okay, so now you see there are two integrals involved here. One is the line integral, and other one is the surface integral of the curve. Okay, so as it happens also in the Green's theorem, that sometimes it's easier to evaluate the line integral, or sometimes it may be easier to evaluate the surface integrals. Okay, so you have to see that what is easier to perform, and then you try to compute the things accordingly. All right, so here the vector field is given by this, and here the component functions are there, just polynomials in x, y and z. so it's fine, because all the continuity and the partial derivatives, everything makes sense. And the surface is given by the paraboloid. Okay, so this is a paraboloid, and this is above the plane z equal to 1, okay, with positive orientation. So now you know what is positive orientation, but we need to be careful little bit, because when we are saying this this is paraboloid, so you have to imagine the paraboloid, and this is also this is lying above the only that part you are interested in, correct? So you see that x square plus y square equals to 5, that is when the z is 0, correct? So let me show you the picture. Yeah, so you are basically here. Okay, this is the paraboloid. Okay, so if I am having at the if I have x and y to be 0 here, then I get z equals to 5. Okay, so this is like a bowl, or upside down, and this is cut by this plane. So you are only interested part of this thing which is above z equal to 1. Okay, so this is the plane, this one, this. So this plane is going to give you the boundary curve. Okay, so this is like a hollow thing, and the boundary is this, and we are considering the positive orientation. Okay, so now you have to go back to the definition of oriented or the positively oriented surfaces. Okay, what we have, we need to think of the direction of the normals away from the solid which it encloses, isn't it? So for that I need a closed surface. Okay, so this right now, this is yeah, I have written it over here. So we need to compute the integral if I use the Stokes theorem. So in order to compute this, I need to compute this. Okay, so for doing this, we need to find the boundary curve of this surface with positive orientation, and the surface as it's given, that this is given by the paraboloid. Okay, and notice that here the boundary curve we know, and it's positive orientation. So you can, as I was explaining, that the region should lie inside, correct? So the positive orientation is going to be this way, and it is going to give you this positive orientation, because if I walk along, the normal should be, your head should be pointing in the direction of the normal vector, correct? So this all you have to write when you try to solve these problems. Okay, so okay, how does one find this equation of this? Because now we have to write down the parameterization, because we have to compute the line integral, because we are so whenever you have such a question, they say that you compute this using Stokes theorem. Okay, this means that you compute the other part in the Stokes theorem to reduce the value of this. Okay, this is so if you start computing this directly, then no, you are not using Stokes theorem, you are just computing it. Okay, so when I set z equals to 1 over here, then you get x square plus y square equals to 4. So that means this circle in the z equal to 1 plane is basically of radius 2, and you can write down the parameterization of that. So you see here z equals to 1, because this is in the space, this is not in the xy plane. So you get the k component here, but that is just constant throughout because of z equals to 1. Okay, so you move full round, so you get a circle, and the parameter theta is going to vary from 0 to 2 pi. Okay, and now all you have to do is just write down this. So f dot dr you write in the parametric form. This is f evaluated at the curve, and the derivative of that curve, take the dot product, so you compute that. Okay, here you should be careful. I just wrote the final answer, and if it doesn't if you get something else, let me know. Okay, because I did not write these steps here. All right, so but the whole idea is like how to consider the orientation, that you have to be careful, because every time you will hear that the orientation is given in the given problem, it is always you consider the upward unit normal. Okay, so depending on the surface, how does the surface look like, and then you decide that what is the induced orientation, okay, on the boundary curve. Okay, so this is how you can use Stokes theorem to compute surface integrals, which can be highly complicated, and they can be computed just using a line integral. Okay, all right. And now we are going to discuss the second part, which is the divergence theorem. So if you remember, in Green's theorem we had the second form, which we call the divergence form of Green's theorem, isn't it? So what did it do? It basically gave us that the integral of the divergence of the vector field over a domain in R2 was related with a line integral. Okay, so something similar we are going to do now in R3. Okay, so what we are going to do, we are going to have a solid region in R3. Okay, and we will consider the triple integral of the divergence over there, and we will say we will get this thing. This divergence theorem basically will give us that the triple integral over a three-dimensional solid body can be obtained in terms of a certain surface integral. Okay, so you look at the boundary of that solid. This is going to be a surface in R3, a closed surface in R3. So this is what this Gauss. Okay, some books will have this Gauss, some books will just say the divergence theorem. Okay, so okay, this is kind of the higher dimensional or three-dimensional analog of that theorem which we discussed. Okay, and another thing, we had considered the triple integral for certain kinds of domain. Okay, we did not have any arbitrary domain over which we had discussed the triple integrals. You remember when we discussed the triple integrals, the domains or the solid regions over which we did this, they were always bounded between two surfaces. Okay, so we will always have that in mind, that we are going to consider only those domains which we could deal with, that Fauven's theorem and so on. Okay, so that will always be there, and in fact, you know, in books they also call such regions as simple region or simple closed regions in R3, or simple solid regions in R3. Okay, so I am not throwing those terms here, but our understanding is very clear that only the domains which we could deal with while studying the triple integral. Okay, so you consider such a domain or a solid region in R3. Okay, and let us say that S is the boundary surface of this solid region. Okay, and of course you assume that this boundary, or you give it the boundary the positive orientation. Okay, so then what we can do is you consider a vector field such that its component functions have continuous partial derivatives on a slightly larger region containing this solid. Then the triple integral over this solid region of the divergence of the vector field is same as the surface integral of the vector field over the boundary surface. Okay, so now you know, by now you know what is the surface integral, isn't it? So, and I mean, you can rewrite this thing. So if you rewrite this is nothing but f dot the outward unit normal, and then ds, the surface area component. Okay, I mean, this again, this is a remark which we are by now very much familiar, that if you have got more than one solids, this theorem can be written down for, you know, finite union of solids which have of same, I mean, the same type that we can deal with. Okay, so let me give you an example here. So Gauss use Gauss theorem to or the divergence theorem to evaluate the surface integral. Okay, so as I said, you know, sometimes evaluating surface integrals can be very difficult because you have to write down the parameterization for the surface. Okay, and if you change the shape a little bit, then that's going to be a problem. So but sometimes it can be easier to compute the triple integrals. Okay, all right, so it depends on the problem which we are at hand. Okay, so what is the vector field here? Again, the vector field is very nice because everything is just a polynomial in x, y and z. You recall, I mean, just notice that here I am writing the surface as S1 for some reason. Okay, and the boundary surface is given by this hemisphere with positive orientation. So this is a sphere of radius 2 and above the xy plane. Okay, and the positive half space. So this is the part, I mean, half of the sphere. So this is the upper half part of that sphere, and we call it hemisphere, isn't it? Okay, so you can easily But there are two things which you need to be careful about. You remember in the statement we talked about the solid region and then the boundary. So the solid region is going to have a boundary surface, a closed one, isn't it? Now this one, this is the part of the surface, but you know the bottom is missing. So this is not a closed surface. So what we have to do is, in order to apply the Gauss divergence theorem, we need to get hold of the closed surface. Okay, so the region which it encloses this hemisphere, you look at that and then cover it from the below. Okay, so this is what it is. So this is the surface which is given to us, but then it is missing the bottom part. Okay, so we have to add that in order to apply our Stokes theorem, the divergence theorem, isn't it? Because I need a closed surface. So what you do, you attach this cover or the bottom and call that S2. So this S2 is precisely a disk in R2, isn't it? And then consider the surface as S1 union S2. Okay, now on this surface, this is going to bound, or this is going to enclose the solid of inside this, and then I can have the relation that the surface integral over S is going to be the divergence of the vector field, and then there is going to be triple integral over the upper half of this ball now, isn't it? Because this is going to be half of the ball. Okay, the solid one. Okay, and positive orientation is going to be basically, so these are going to point outward. Okay, but you know the normals point outward, so when you are at the bottom, outward is going to be this. Okay, so actually this is, I should have drawn a proper one. Okay, and this is you know, this is plus k and this is the negative of that, isn't it? So this I can, yeah. So you see, if we were not careful and then directly apply Stokes theorem and conclude that the integral, certain integral over S1 is going to be the triple integral of the divergence, then that's wrong. Okay, so now what we have to do is, we have to apply the divergence theorem on the surface S, which is the union of the paraboloid, and then the you know, put the disk in the bottom, and you know that the integral is a linear process, so it's going to give you two integrals. Okay, so in order to do this, I have to compute, I am interested in computing this, so I have to compute this and as well as this, so that I get this. Okay, now okay, so let us first compute the triple integral. So divergence you have to compute for that. Now this guy, you see the vector field here, you have to take the partial derivatives of P, Q and R. Okay, so partial derivative of this is going to be with respect to x, so you get just 1. This with respect to y, so there is no y here, so 0, and with respect to z here, so there is no z here, so 0. So the divergence is precisely a constant here. You know, this is a simple example, but the idea is important. You know, even though the computation will be simple in this, but it has a nice idea, so that you don't make mistakes. Okay, so if I have to compute now the divergence, which is 1, a triple integral of the constant 1 over the half of the ball, what is it going to be? It's just going to be the volume of the ball divided by 2, isn't it? So this is precisely, so what you know the volume is 4 pi by 3 and then r cube. Okay, so this is just going to be 2 pi by 3 r cube, and what is r here? R is the radius. Okay, so I think it was 2, and you get 16 pi over 3. Okay, so this is how, so this becomes so easy, we didn't really have to do any integral. Okay, and now we need to compute the other integral, which is coming out by, because we had added this extra part to get a closed surface, and hence we could apply the divergence theorem. Okay, so we now need to compute this guy also, and this is a flat surface. So flat surface, so that means this surface integral is actually a double integral. Okay, and this integral is over a disk. So you know that whenever you are dealing with integrals over disks, then you just do the polar coordinates, and you also know that because of the positive orientation, the normal vectors you have to consider as minus k. Okay, so all that you put together and write down this double integral, use polar coordinates. Okay, so f dot minus k is just going to be negative of x square. You go back to the form of this vector field and only the z component going to come in, and just substitute things. So this is a disk of radius 2 and you get this integral. So please verify it, okay, and hence the integral which you are interested in, the surface integral over the part of the paraboloid, it's going to be this volume integral minus the thing which you had added, okay. So I am getting this answer, so you please verify this, okay. So this is how you have to use these two theorems to simplify the integrals which you are dealing with. But you have to be careful that if you don't have a closed surface, then you have to make it closed first in order to apply the divergence theorem, for example, okay. So I will stop here, and as you know that this is the last lecture of this course. I hope you learned something in this course. Of course it was I cannot really expect that you learned everything, because I myself didn't really enjoy it, because there is no feedback from your side, and I'm just talking to myself all the time. So I don't know what happened, but I will be happy if some of you have learned a little bit or have found something interesting. And you are always welcome in the future, that if you want to come and discuss over anything from the course or other things. So very good luck for your final exams. I think all of you are doing this excellent. So okay, see you then.